Hello again, AP Physics 1 students. If you're still with me for this video, you have not yet quit. Excellent. So the problem we're going to look at now is one in which we'll be using the two kinematics equations that we introduced in the last video. I'll remind you of what those were, of course, but this problem appears in the kinematics packet, just like everything else we've been working through, and it's the page called The Race. So let's see what this problem is all about. So an octopus starting 100 meters north of the harbor, okay, swims at a constant 5 meters per second south. Suppose there is a marlin located 600 meters south of the harbor, initially moving at 2 meters per second north and accelerating north at 4 meters per second squared. Suppose the animals travel along two slightly different paths, so they don't hit each other when they are at the same x coordinate. So we have some questions that we want to address here, like who will get to the harbor first? How fast will the marlin be moving when it reaches the harbor? Where will the two animals actually meet up and pass by each other? And then we also want to construct position, velocity, and acceleration versus time graphs for the two separate animals. Okay, so in a problem like this, the first thing you need to do is kind of draw a little diagram for yourself, right? To get an idea of where objects are starting out and where they're located. That is, where they're located and how fast they're moving initially. So I'm going to draw my little x-axis over here. And I don't want to put the units of meters on all the little tick marks. So I'm just going to indicate by the label here that the x coordinates are being measured in meters. All right, now the origin of the coordinate system is x equals 0. And we have to decide, do we want to place any either of the characters, for instance, at x equals 0? When I read this description, it kind of suggests to me what I should position at x equals 0 to make my life a little easier. Pause the video and try to figure out what should we consider to be located at x equals 0 for our own ease of calculation. All right, hopefully you said the harbor. The octopus is north of the harbor, the marlin is south of the harbor. The positions are given, the initial positions of the two animals are given relative to this thing called the harbor. So we should place the harbor at the origin of the coordinate system. So I have a little picture here of the Redondo Beach, like marina sign. And oh, look at that. I've got my two characters behind there, the marlin and the octopus. Let's shrink all this down. So the harbor is located at x equals 0. And it says that the octopus is 100 meters north of the harbor. Look at that cute little guy. I'll shrink him down. The octopus is located 100 meters north of the harbor, let's say over there. And the marlin is located 600 meters south of the harbor. So the marlin's significantly further away than the octopus is to start. So let me indicate that the octopus is at 100 meters and the marlin is at negative 600 meters. Note, I'm considering the positive x direction to point north and the negative x direction to point south. All right, in addition to labeling where the two animals start, it's useful to label in the diagram what the initial velocity of the two animals is. So this octopus swims at a constant 5 meters per second south. So it has an initial velocity of 5 meters per second, and it's got no acceleration. So its acceleration is 0. On the other hand, the marlin has an initial velocity which is rather small, the initial velocity of the Marlin is just 2 meters per second, and it points north based on the indicated by the arrow that I drew there. And the Marlin has an acceleration of 4 meters per second squared north. All right, so I've indicated the initial positions, the initial x coordinates, and the initial velocity values, and the constant acceleration values for the two characters. I'm going to remind you now of the two kinematics equations. So the first is this one, that the final x coordinate of an object is just equal to the object's initial x coordinate plus its initial velocity times time plus 1/2 its acceleration times time squared. This is kinematics equation 1. And also that the final velocity of an object is equal to its initial velocity plus acceleration times time. This is equation 2. And recall that these kinematics equations only work for constant acceleration motion. Thankfully, both of these characters do have a constant acceleration, 0 meters per second squared for the octopus, and 4 meters per second squared is the constant acceleration for the Marlin. So question number 1 is, who will reach the harbor first? And the reason that this question is somewhat compelling is because, look, we have the octopus just 100 meters from the harbor and swimming toward the harbor at 5 meters per second. On the other hand, the Marlin is a much larger 600 meters away, and the Marlin is initially only swimming at 2 meters per second toward the harbor. But the Marlin is going to be accelerating at 4 meters per second squared. Because the Marlin is accelerating to the right and also initially moving to the right, it will speed up. When velocity and acceleration both have the same sign, when they both point in the same direction, as is the case for the Marlin, then the Marlin speeds up. So maybe the Marlin can speed up sufficiently fast to bridge the gap between, cover that extra distance in less time than it takes the octopus to do so. All right, so let's go to work here. So question 1, who will reach the harbor first? We want to know who reaches the harbor first. That is, who reaches the harbor in less time. Take a moment to think about which of the kinematics equations you might use to determine which character reaches the harbor in the least amount of time. You can pause the video. All right, equation number 1 is what we need over here. Equation number 1 deals with the position as a function of time. And the key here is that whoever has a position of 0, that is, whoever is located at x equals 0 in the least amount of time, that's the person who reaches the harbor first. So maybe we first look at the octopus. Ordinarily, I would rewrite this kinematics equation with the variables. In fact, well, I'm not going to do it here because I already wrote it down, but I would ordinarily, in a solution, write down the kinematics equation with the variables to start. In this case, I won't. I'll just start plugging in values. So the final, you know what? I will write it down. So kinematics equation 1 for the octopus. Okay. All right, now what? Can I simplify this a little bit? I can. The octopus has no acceleration, so I'm just going to indicate that that last term in the equation is 0. And we want to find the time at which the octopus is located at with a final x coordinate of x equals 0. So I'm going to plug in x equals 0 for the final x coordinate of the octopus. The initial x coordinate is 100 meters. The initial velocity, this is really important, is -5 meters per second. And then I multiply by time. So I've customized kinematics equation 1 for the octopus. Its initial velocity is -5 meters per second, and it has no acceleration. Once I plug in my numbers with the units, and you should plug in with the units, you can then remove the units for ease of calculation. I think you can see here that t equals 20 seconds. So the octopus makes it to the harbor in 20 seconds. How about the marlin? How about the marlin? Same thing. Kinematics equation 1 will allow us to find the time at which the marlin reaches the harbor. If it's more than 20 seconds, I guess the octopus wins. If it's fewer than 20 seconds, the marlin wins. So let's set x final equal to 0 for the marlin. X initial is negative 600 meters. The initial velocity of the marlin is positive 2 meters per second. So positive 2 meters per second times time, plus 1/2 the acceleration, which is positive 4 meters per second squared times time squared. And we can simplify this a little. 0 equals 600. I'm removing the units now. Plus 2t plus 1/2 times 4 is 2t squared. And if we wanted to, we could simplify this again by dividing each side of the equation by 2. And we get the following quadratic equation. 0 equals negative 300 plus t squared. You can solve this any way you want. You can apply the quadratic formula. If your calculator has the ability to do this quickly, you can use your calculator. However you do it, you will find that the time at which the marlin reaches x equals 0 is 16.8 seconds. Now, there's actually 2 roots to that quadratic expression, but one of them is negative. Mathematically, it makes sense that there's 2 roots, but because one of the roots is a negative time, it doesn't make any physical sense. So the whole process starts at the time that I'm calling t equals 0. Any time that I solve for, which turns out to be negative, is not the time I'm looking for. That's physically reasonable given the problem. All right, so the marlin makes it there 3.5 seconds before the octopus makes it, not 3.5, 3.2 seconds before the octopus makes it there. It looks like the marlin wins this race. Okay, so the marlin makes it there first. Now, let's look at question 2. How fast will the marlin be moving when it reaches the harbor? So take a moment to think about how you would handle that. How fast is the marlin moving when it reaches the harbor? First of all, which kinematics equation do you think you should use? Pause the video and figure it out. Okay, hopefully you identified that when we're asking how fast, we're really interested in like speed. I actually don't care about direction when I say how fast in this context. The marlin, we know, is always swimming north. So how fast is it moving? I want to know at how many meters per second it's moving when it rushes by the harbor. And you need kinematics equation 2 to take care of this. So I'm going to shift this up and make space for the next solution here. All right, so we're looking at the marlin, and we want to know how fast it's moving when it rushes by the harbor. Kinematics equation 2 says the marlin's final velocity is equal to its initial velocity plus its acceleration times time. And I want to find the final velocity of the marlin, where by final, I mean when it passes the harbor. So the marlin's initial velocity is 2 meters per second. The marlin's acceleration is 4 meters per second squared. And then I have to multiply acceleration by time. Well, we just found in the previous problem that the time at which the marlin flies by the harbor is 16.8 seconds. So if I do the calculation here, first of all, note that the first term has units of meters per second already. The second term has units of meters per second squared times seconds. But that means one factor of seconds goes away in the numerator and the denominator of those units there. So both terms do have units of meters per second. I can solve this, and I find that the Marlin is zipping by the harbor at 69 meters per second. Oh, I should write up here that the Marlin wins. Marlin wins. Marlin gets to the harbor first. And this is the speed at which the Marlin shoots by the harbor. Note, it started moving at only 2 meters per second north, but over the course of those 16.8 seconds and that 600 meters of northward travel distance, the Marlin is moving very, very fast in this story when it shoots by the harbor. Okay, let's take a look at question 3. So in question 3, it says, where will the two animals pass each other? All right, where is a question about position. In other words, at what position, at what location, where will the two animals pass each other? Because they are going to move by each other. They won't collide, but they will be at the same place at the same time in terms of their location on the x-axis. Pause the video and think about how you would go about finding out where the two animals pass each other. All right, so maybe you were able to figure out that kinematics equation 1 is what we need again. Kinematics equation 1 gives us the position of each animal at any time we plug in. And we need to make use of kinematics equation 1 in order to figure out the position at which the animals coincide. So let's see. We have these equations already customized. For the octopus's final x-coordinate is equal to the octopus's initial x-coordinate, which is 100 meters. I'm going to leave out, I'll put in the units, 100 meters, plus its initial velocity, which is minus 5 meters per second times time. And for the Marlin, its final x-coordinate is equal to its initial position, negative 600 meters, plus its initial velocity of 2 meters per second times time, plus 1/2 its acceleration times t squared. Now here's the key. If we set these final x coordinates equal to each other, that's equivalent to setting the right sides of these equations equal to each other as well. We can first find the time at which the two animals are at the same location. Then we can plug that time back into either version of equation 1, either for the octopus or for the Marlin, to figure out the position where the animals are located. So let's do that. Removing units, the octopus's final position is 100 minus 5t, and we're going to set that equal to the final position of the Marlin. Again, removing units is negative 600 plus 2t plus 1/2 times 4 is 2t squared. I could move all of this stuff over to the right side of the equation, and I get negative 700 plus 7t plus 2t squared equals 0, of course. All right. Again, apply the quadratic formula or use a method of your choice, and you will find that t equals 17 seconds. Let's just see if that makes sense. 17 seconds. So the Marlin gets to the harbor at 16.8 seconds. At that time, the octopus is going to be very close to the harbor, but not quite there. And then 0.2 seconds later, from 16.8, 0.2 seconds later is 17 seconds. The Marlin and the octopus are now at the same location. But the octopus doesn't get to the harbor until 3 seconds after that, 20 seconds. So far, this is all very comforting. The Marlin gets to the harbor first at 16.8 seconds. Then the Marlin and the octopus are in the same location at 17 seconds. And finally, at 20 seconds, the octopus finally shoots by the harbor. let's see what position this corresponds to. So we can take this 17 seconds and plug it into the simpler of the two position equations, for the octopus, that is. The final position of the octopus is 100 minus 5 meters per second times, if I plug in the 17 seconds, I get that at 17 seconds, the octopus is located at x equals 15, so 15 meters, which is somewhere around here. All right, I didn't set up the pictures in the exact right spot. I don't think I have the ability to, yeah, I kind of can move them where I want. So right there, at 17 seconds, when the octopus and the marlin are in the same location, they are at x equals 15 meters. This is very comforting again. The fact that they're meeting up at a positive x coordinate, that is, they're meeting up to the right of the origin, tells me that everything is consistent with the previous timings that we've already discovered. Okay, finally, we want to make graphs of position, velocity, and acceleration for the characters. So let's do this together. First, I'll set up some axes, and then we will plot the position, velocity, and acceleration for the two characters on, you'll see what I mean when I say on common sets of axes. So that's one. I'll duplicate. And I'm going to zoom out a little bit. And I'm going to duplicate again. Okay. Perfect. And now I'll zoom back in. I'm really loving this new Zoom whiteboard. So this updated version. Okay, so the bottom graph will be acceleration versus time. The middle graph will be velocity versus time, and the upper graph will be position versus time. And unless you want to put the units down on every like tick mark that you make, you should put the units near the variables. So meters per second are the units of velocity, meters per second squared are the units of acceleration. Let's start with the easiest graph first. The acceleration is always the easiest graph to do first. So I'll stipulate that I'm going to use red for the octopus, and I will use this, what's called dark purple, for the marlin. So the octopus will be red, the marlin will be dark purple. Okay, well, the octopus has an acceleration of 0. So, I have to adjust the color. The octopus has an acceleration of 0. So for the octopus, its acceleration versus time graph is just a flat line at acceleration equals 0. It just coincides with the time axis. For the marlin, the acceleration is a constant positive 4 meters per second squared. So I'm going to plot that as well. So for the marlin, 4 meters per second squared is the acceleration. So that's simple enough. Both characters have a constant acceleration, with the octopus having a constant acceleration of 0. So it's not really accelerating. All right, now let's look at the velocity plots. So for the octopus, the velocity is a constant value. The octopus moves at a constant velocity of -5 meters per second. So I'm going to plot that, and I'll label it -5. I actually don't need to label the units because as I said before, I labeled the units here and here already. So the octopus has a constant velocity of -5 meters per second. The marlin starts with a velocity of 2 meters per second. But then its velocity gets larger and larger and larger, right? In fact, by the time it reaches the harbor, its velocity is 69 meters per second, we figured out. So the Marlin's velocity is going to become increasingly positive, starting at 2 meters per second, but increasing. Because the acceleration of the Marlin is constant, the acceleration is the rate at which the velocity changes. So a constant acceleration for the Marlin means a constant rate of change for the velocity of the Marlin. And that means a constant slope. Rate of change corresponds to slope when you're graphing something versus time. So try to appreciate what's happening here. Constant negative velocity for the octopus, and the Marlin's velocity is positive. The Marlin's moving north or to the right, and its velocity is getting larger over time at a constant rate of 4 meters per second, which is the acceleration of the Marlin. All right, finally, the position. So let's think about the octopus. The octopus starts at x equals 100. So x equals 100 meters is the initial position of the octopus. And the octopus is moving south. It's moving in the negative direction. It's going to eventually pass x equals 0 when it flies by the harbor. What does the graph look like? Well, the octopus's velocity has a constant value of -5 meters per second. But the velocity of an object is the rate at which its position changes. Therefore, the position, got to adjust the color. Therefore, the position of the octopus changes at a constant rate of -5 meters per second. This time right over here is the time at which the octopus has an x coordinate of 0. And we know that that is 20 seconds. That's the time at which the octopus reaches the harbor. All right. Let's think about the Marlin's position versus time graph. So the Marlin has an initial position of -600 meters. And the Marlin is going to move in the positive x direction. So I know the graph has to increase somehow because the Marlin has to get to the harbor and then shoot by the harbor. Now, unlike the octopus, the Marlin doesn't have a constant velocity, right? The Marlin's velocity is getting bigger and bigger and bigger over time. That means the rate at which the Marlin's position is changing is getting bigger and bigger and bigger, which geometrically means the slope of the Marlin's position versus time graph is getting bigger and bigger and bigger. This is describing a parabola that looks something like this. In fact, let me try to make that a little cleaner. Yeah, not bad. A parabola which looks something like that. The slope of this parabola is not 0 to start. The slope of this position versus time graph for the Marlin starts at 2 meters per second, because that is the initial velocity, the initial rate of change of position for the Marlin. So we're not starting at the bottom of the parabola here. We're starting on the upslope. This time, right here, let me zoom in. Very nice. This time is the time at which the position of the Marlin reaches 0. That is the 16.8 seconds it took for the Marlin to reach the harbor. And this is an important time over here. This time, where the Marlin's and the octopus's position functions intersect, that's the time at which they have the same position. we know from our previous calculations that that's 17 seconds, and that occurs at 15 meters. So think about that. They're both at 15 meters at 17 seconds. So let me just narrate this one more time. What is this image showing me over here? It's showing me that the octopus starts just 100 meters from the harbor, and the marlin starts a much larger 600 meters from the harbor. But the marlin reaches the harbor in 16.8 seconds. Then the marlin and the octopus coincide at 17 seconds, 15 meters to the right, north of the harbor. And 3 seconds later, the octopus finally reaches the harbor. But look, at that time, at 20 seconds, the marlin has some really big X coordinate. The marlin is way off to the right, way past the harbor in the northward direction by the time the octopus finally reaches the harbor. Okay, this is very typical. When you have constant acceleration motion, you get flatlining acceleration versus time graphs because the acceleration is constant. You get at the most complicated velocity graph you'll get is just a linear graph with a positive or negative slope. And the most complicated position graph you'll get is a parabola. All right, so hopefully this video has illustrated for you how to make use of the kinematics equations to solve word problems, to analyze what happens first and where different events happen when you have objects moving in one dimension, and also to show you how graphs of position, velocity, and time can very effectively represent the motion of one or more objects. Okay, see you next time.